Hey everyone, I wanted to make this video on this Friday because I really haven't made just one directly like this in a while. I wanted to go over two very important parts of what we're learning right now in class and hopes that this will make your job a little bit easier. And hopefully, whether you come into class physically on Monday or you are virtual, you will sort of understand what's going on. Okay, so we've been showing ways to represent electrons in atoms. And we went through the different models and we talked about all the way from the plum pudding model um, up to the quantum mechanical model, which is what we use today. So we are going to show how to represent electrons in two ways. We have electron configurations and we have orbital notations. Okay. And so I'm going to compare and contrast the two here, and then we're going to do some examples of these. So it hopefully will help you understand this a little bit better. So for electron configurations, okay, you use superscripts, okay, to represent the number of electrons. That tells you the number of electrons per energy level, okay? Whereas in orbital notations, you use arrows, which represent the number of electrons, and then you also use lines, okay, which represent horizontal lines, which represent the number of orbitals. Okay. In the past couple of days, we have talked about a nice chart that we have used. We've used S, P, D, F. These are the four orbitals that we use. Okay. And the number of orbitals, or numbers, these are the four subshells that we use. The number of orbitals and the number of electrons that are in these four orbitals are as follows: 1, 3, 5, 7, and for electrons, 2, 6, 10, 14. Okay. Now you don't have to use this amount of electrons per orbital, but you can use up to that number. So for instance, you could have one electron in S, and you could have two electrons in S, but you can't have three in S. Okay. So I posted on Google Classroom today on this Friday. Well, first I posted a link to a periodic table, online periodic table that would help you hopefully understand this as long as you go along and mess with it. And we do have an assignment later in the week where you are going to have to click on some stuff in that periodic table. But regardless, I also posted an image of the periodic table as represented by the S, P, D, and F block. And I'm going to show you that in a few minutes, but it's also online as well. Okay. So we're going to represent this with both, okay? Now we have to follow three rules. And we briefly talked about this yesterday, and I'm not sure if I even talked about it in every single class, but we will follow those rules here as well, okay? But if we did not cover that, we will cover it. But I just want to show you the differences between these two today, okay? So for electron configurations, let's say I'm going to pick an element that's more towards the top of the periodic table. So I guess we would go with just go with oxygen. Okay, oxygen has 8 electrons, and we know that by looking at its placement on the periodic table, which is right here. Okay, it has 8 as its atomic number, but it's neutral, so it also has 8 electrons. That's the first thing you must do. You must figure out the number of electrons in all these. Okay, so oxygen has 8. So when you're going through this, okay, you need to know the blocks of the periodic table, S, P, D, F. All right. So I have this to help. Okay. So over here is the S block. Okay. Now the only exception on the periodic table that's placed differently is this element right here, which is helium. And the reason it's placed over here is because it's a noble gas, but it is in the S block as well. Okay. So we can't talk about chemistry without exceptions, but that's the only one. Okay. So oxygen has 8 electrons. So we're going to go in order: 1, 2, 3, 4, 5, 6, 7, 8. This would be oxygen's location. Okay, and to get there, and you can see how these compare right here. Okay, to get there, you have to go from the start 1s, 1, the first element of 1s, 1s, 2. Okay, so we go 1s, 2. Then our next block we go to where lithium is 2s. We go 2 elements in 2s, so 2s1, 2s2. And then we go to 2p. That is the next block that we go to. And you need to look at this like you would be reading a book, okay? You'd go top left to right, and then you go down a line left to right. Okay, remember we have to follow the order according to the Aufbau principle. So we have to go from the ground up, okay? So the ending, and for some reason on this, I don't know why, I just noticed that it doesn't have this block. I have no idea why, but who knows? This is 7p, and this is the last block we currently have. So if you read this, you would start with 1s, and you eventually end in 7p, okay? So anyways, oxygen is right here. So it's 1s2, 2s2, 2p, 1, 2, 3, 4. It is the fourth element in 2p, okay? So we're going to represent that here. Oxygen, its electron configuration, 1s2, 2s2. Okay, that is the order of this. And then 2p, and there are 4 in 2p. You cannot have more than 2 electrons in s. You can have up to 6 in p. We don't have 6. That's fine. We can have 6 or less. All right, but you cannot have more than 6. So that means you'll never write 2p with like 8. Okay, that does not happen. All right. So this is the electron configuration. And these superscripts up here, the 2, 2, and the 4 must equal the number of total electrons in that specific atom. And in oxygen, it has 8. 2 plus 2 plus 4 equals 8, so we're good. Okay? So this is the way to represent it with an electron configuration. Okay? There's another way to represent this. It's called an orbital notation, which is a little bit more difficult to write out. It's just longer to do. So an orbital notation, as we said up here, uses lines, horizontal lines, and uses arrows. The arrows represent the number of electrons, and the horizontal lines represent the orbitals, okay? So if you were to translate this over here, we start with the 1s orbital, okay? So each of these lines represents an orbital. S has 1, okay? So there's one line. Up arrow, down arrow, okay? And that's how we represent it. So some classes have and some classes haven't. We've talked about the spin, or we haven't talked about the spin, but that's represented by the spin, okay? So we will get to that eventually. And I know this stuff is confusing. It's going to be, and I knew it going into this unit that it is confusing, but it's going to take some practice, and it's going to take you actually watching these videos and stuff that I post, whether it's one like this or whether it's one from a class. Okay, you're going to have to go through this stuff to get it. Okay, you cannot just Google search this stuff and understand it. It will not happen. Okay, so anyways, now I put lines here because it helps me separate them, separate the orbitals out. I would suggest you do it as well, but if you don't do it, that's probably fine. But the only problem with that is if you may get all of your stuff jumbled in together, and then it'd be hard to see. Okay, but I would suggest putting vertical lines between these to show where it's separated out. So after 1s here, let me bring this back out. Okay, after 1s, okay, we're in 2s. If we're just reading a book, okay. So this is hydrogen. This one is lithium. This one is beryllium right here. Okay. We're in 2s. There are 2 elements in 2s. Okay. Up arrow, down arrow. Now, if we stopped right now, this would be the orbital notation for beryllium. because there are 4 arrows. Beryllium has 4 electrons. Sorry about all that noise. Beryllium has 4 electrons. Okay, so after 2s on here comes 2p, right? So we read it like a book. 2p1, 2p2, 2p3, 2p4. We need 4 electrons in 2p. Now, every p orbital, not just 2p, every p orbital, as you can see here, they have the same number of total elements in them, 6, okay? But they also have the same number of orbitals, 3. So we need 3 horizontal lines. Even if you don't use up all the orbitals, you still have to draw it like you would, okay? And you'll see that in a moment when we do a few more. So for 2p, we need 4 electrons, and electrons are represented by arrows. Now, we have either talked about this rule yet or we haven't, but regardless, we are going to. This is called Hund's rule. You must go have these spins in the same direction, all of them, before you put one in an opposite direction. That is a rule you must follow when writing these, okay? It's just a rule. So we must follow it. It's called Hund's rule, okay? Hund's rule. So if we haven't got to that, we will get to it. But anyways, that is the rule we must follow when filling out these orbitals. So if you add up the number of electrons here, or arrows, I guess, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 arrows, 8 electrons. That is the number of electrons oxygen has. Okay, so that is for oxygen. Now we're gonna do a different one. Okay, I'm gonna pull out a paper I have. Okay, that I just printed out. And we're going to go through these. We're not going to do the orbital notations for these right now. We're going to stick with the electron configuration, and then we'll do a few more orbital notations before this video is over, okay? So for each of these, we need to look at the periodic table, and we've already done oxygen, so I'm going to skip that one. We need to figure out how many electrons it has. That is the first step to doing anything. If you do not know the number of electrons, you are not going to do it correct, okay? So for lithium, and it helps when you're practicing this to actually have a periodic table. Okay, so lithium has 3 as its atomic number, so it has 3 electrons. All right, so lithium is the 3rd element in the periodic table. Okay, it is right here. So we always start with 1s, and looking at this, lithium is right here. So to get there, we go through 1s, 2, and that's the first element in 2s. So it's 1s2, 2s1. And if you add those superscripts up, 2 plus 1 equals 3. That is the number of electrons in lithium, okay? So let's move on to calcium, which is a little bit farther down the periodic table, okay? Calcium is right here. Calcium has 20 electrons, okay, because its atomic number is 20. So 20. We need to show 20 up here, okay? So this becomes kind of redundant the more you do it, because you always start with the same thing. You always start with 1s2, and then you're always going to go to 2s. Now, we need to fill it up with 2. Remember, we can have 2 electrons max in an s orbital. We have to fill it up with 2 because we have to go farther than that, okay? So after 2s2 here comes 2p, okay? And we know calcium has 20 electrons. Right now, we only have 1, 2, 3, 4. So we need to go farther. 5, 6, 7, 8, 9, 10. We still need to go farther. 11, 12, over here, 13, 14, 15, 16, 17, 18, 19, 20. This right here, where I put the X at, is where calcium is. So it is the second element in 4s. So it ends in 4s2. So we know it ends in 4s2, so we need to get there. Okay? So after 2s2 comes 2p. There are 1, 2, 3, 4, 5, 6 elements in 2p. 2p6. Okay? After 2p6, okay, comes 3s. There are 2 elements in 3s. We have to cross both of them. So 3s2, back looking at this, we're over here. There are 6 elements in 3p, okay, and we have to cross all of them to get here. Okay, so that's going to be 3p6. Now if we add up these superscripts, 2, 4, 10, 12, 18, we need 2 more, and the 2 more are in 4s2. Okay. That is the electron configuration for calcium. Okay. So I'm going to skip down and go to potassium. I'm going to show you how this, prove to you how this becomes kind of redundant, like I said, after a while. Okay. So potassium, if you look on the periodic table, potassium is right here. It's 1 before calcium. It has 19 electrons. 19. Okay. So the only difference between potassium and calcium is right here. Potassium is 1 before it right here. Okay. So this right here is potassium. So potassium ends in 4s1. It's the first element in 4s, but everything else before that is the exact same. So you start from the bottom up. It's the same. Well, it's the same. Okay. The only difference here is this is 4s1. It is one less. It's one less in that block. Okay. We're going to do one more before we do one more orbital notation and call it a day. Okay. So we're going to do chlorine. Chlorine has 17 right here as its atomic number. So it's 17 electrons. Remember, that's the most important step. So we need to show 17. Now chlorine is right here, 17. So let's look at this one and let's count over 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right here is chlorine. Okay. So it is the 1, 2, 3, 4, fifth element in 3p. Okay. So we know it ends in 3p5. So everything else is the same before that. It's just the same. It's the same path to get there. This ends in 3p5, not 3p6, because we don't fill it up completely. Okay. So 2, 4, 10, 12, 12 plus 5 is 17. Okay. So I'm going to do an orbital notation for chlorine real quick, and that will be the end of this video. Okay, and we'll be practicing this quite a bit next week. So chlorine. Let me put it where you can see it. Okay, chlorine here. Now, this was its electron configuration that we just did. Okay. Turn this. That's fine. So chlorine here, we have to show this like this. Okay. So S has 1 orbital. We need both electrons in it. 2s has also 1 orbital because it's s. The number out front does not tell you the number of orbitals. It is the letter SPD or F. Okay, the number out front is your principal quantum number. So next is 2p. There are 3 orbitals for p. Now we have to fill up this. So we go up, 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 down, down, down. Okay. After 2p comes 3s. S has 1 orbital. We have to fill it up because we need to go past 3s. We need to go to 3p5. So 3p, 1, 2, 3, 3p. There are 3 orbitals, not because of that 3, because p has 3 orbitals, every p. 2p, 3p, 4p, whatever has 3 orbitals. We need to show 5 electrons here. So we go up, 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 down, down. Okay, so this is the orbital notation for chlorine. Okay, so hopefully this